All right, so here's a reflective surface such as a mirror. And then this is what's called a normal line. The word normal means perpendicular. So a normal line is a line that's drawn perpendicular to the surface of the mirror. Light coming towards the mirror is called incident light. And here's an incident light ray hitting the mirror. The light that bounces off the mirror is called reflective light, which is represented by a reflective ray. And here I'm going to relate two angles. One is the angle of incidence, theta sub I, that the incident ray makes with the normal line, not with the mirror itself. Theta sub r is the angle of reflection, which is the angle the reflected ray makes with the normal. The law of reflection states that these two angles are equal to each other, so the angle that the incident ray makes with the normal line is going to be equal to the angle that the reflected ray makes with the normal line. The arrow shown here represents an object being reflected by the mirror. I'll make an incident ray that comes from the top of the arrow to the mirror, and the angle of incidence here is 20 degrees, so that's also the angle the reflected ray makes with the mirror. Now I'll make another incident ray angled downwards, and again it reflects with the same angle. Now an image is going to be formed where the reflected rays converge, but even if I continue these reflected rays, they're never going to converge. So what I have to do here is extend the reflected rays behind the mirror, and I'll find that they do converge somewhere behind the mirror, and that's the location where the top of the arrow's image is going to be. One thing about this image is that it's what's known as a virtual image, since there is no actual location inside the mirror where the image appears. Instead, the reflected rays appear to originate from a single point that's inside of the mirror. Constructing a complete image often involves reflecting multiple points on the object. A faster way to construct images on a flat mirror is to use horizontal incident rays. So the angle of incidence is 0, so it'll reflect back on itself since the angle of reflection will also be 0. Any image on a flat mirror is going to be flipped horizontally, as is the case with the arrow here. Overall, images in a flat mirror are pretty straightforward. The image size is going to be the same as the size of the object, so the heights of the two are equal. And then the distance that the image appears to be from the mirror will also be equal to the distance of the object to the mirror. And then for flat mirrors, all the images are going to be virtual and upright. So that's flat mirrors. There's also spherical mirrors, which are a section of a spherical surface. They have a focal point inside their radius of curvature, and that focal point is 1/2 the distance from the center of curvature to the mirror, or 1/2 the radius of curvature. And first I'm looking at concave mirrors, where the reflective surface is on the inside. Now, drawing reflected rays on a spherical surface is a bit more complicated. Even though the law of reflection still holds true here, the surface is now curved instead of flat. So in this case, we have to use what are called principal rays. There's 3 principal rays, but you're only going to need 2 of them to construct an image, since all reflected rays will converge at a single point. The first principal ray is one that travels straight horizontally to the mirror, parallel to the central axis, and this ray reflects through the focal point of the mirror. On the other hand, the second principal ray travels through the focus first till it gets to the mirror, and then travels in a straight line parallel to the central axis. Then there's the third principal ray. This one goes through the center of the mirror, and then it reflects back on itself through the center of the mirror again. Again, the image is going to be where the reflected rays converge. And here I'm looking at an object for a concave mirror placed beyond the center of curvature. In this case, the image is going to be real, since the reflected rays actually do converge outside the mirror. But now the image is also inverted, since it faces upside down. Now, as I get closer to the mirror, the size of the image will increase. So if I place the object at the center, the image will be the exact same size as the object. And here again, the image is inverted. And it turns out that all real images will be inverted. If I go beyond the center of curvature, but still outside the focus, the image will become enlarged. And concave mirrors are often used to enlarge objects, although the image here will still be upside down. When an object is placed at the focus, the rays don't converge. And even if I continue the rays beyond the mirror, the rays will still be parallel and will never converge. So in this case, there is no image formed. And then when I move within the focus, the reflected rays don't converge outside the mirror again, but now I can continue the reflected rays behind the mirror. And here I'll find that they will converge and produce a larger upright image. And in fact, all virtual images will appear upright. For a convex mirror, it's the outside surface of the sphere that is reflective, and here the focus is within the mirror. The principal ray rules are the same, but now they just pertain to the focus and center on the other side of the mirror. And then all images in a convex mirror will all have the same properties, which are they are smaller, they're upright, and they're virtual images.
Mirror. Mirror on the wall. Who is the fairest subject of them all?
Chemistry. You are truly one of the subjects of all time, but none are fairer than physics.
NANI?!